Okay, so it's time to start our option, which is energy. We're going to talk about energy sources and fossil fuels. All right, so first the usefulness of energy. Quality energy sources are those that contain a lot of potential energy per unit volume, and they can be transferred into useful forms at a reasonable rate with minimal pollution. So when we say a reasonable rate, if the energy is produced too fast, it's difficult to capture. Kind of like in a nuclear explosion, the energy is released too fast, so all it can do is destroy. If it's released too slow, then we won't get enough energy per unit time to make it useful. So here's an equation for the combustion of glucose. So we can combust glucose in a number of different ways. We can just burn it in a calorimeter and release the energy that way, or we can eat stuff and process it in our body. And you can see the carbon dioxide that's released in this reaction is actually the source of the carbon dioxide that we exhale when we breathe. All right, so we have the bomb calorimeter and the human body. Now, if we combust 1 mole of glucose, the same amount of energy will be released whether we do it in the calorimeter or in the human body. But in the calorimeter, it comes out too fast, so it won't be useful to human beings or to any kind of life. Then the human body, the energy is released at a much slower rate, so our bodies can make use of it. All right, so we can quantify the quality of energy with energy density and specific energy. The energy density is the energy released per unit volume of the fuel. So again, the more energy we have per unit volume, the higher quality the fuel is. Now, energy density can be calculated with this formula. This formula is in the data booklet. It's the energy released from the fuel divided by the volume of fuel. Now, generally, when you're given problems with energy density, they're not going to be as simple as a problem that gives you the energy released and the volume of the fuel. Right? So instead, what they're going to generally do is give you a density and a value for delta H. So if you are a guru with units, you will know that multiplying the delta H value by the density and dividing by the molar mass will ultimately give you a unit of energy per volume, usually kilojoules per liter. Right? But if you're not a guru with manipulating units, it's probably just easier to remember that energy density can be calculated by multiplying the delta H value by the density and dividing by the molar mass of the compound. And specific energy is the amount of energy per unit mass. So they're very similar but a little bit different. And specific energy can be calculated using this formula, energy released divided by mass. So again, this formula is given in the data booklet, but generally, if you're given a delta H value and you know the fuel that's being consumed, you can calculate specific energy just by dividing the delta H value by the molar mass. All right, so let's look at a little bit of practice. It says the standard enthalpy of combustion of carbon is negative 394 kilojoules per mole. The density of anthracite is 2,267 kilograms per cubic meter. Now, use this information along with the relative atomic mass of carbon to calculate the energy density and specific energy of this form of coal, assuming it to be 100% carbon. So use the information on the previous slide to go ahead and solve these problems. Pause video. Alright, so the problem gives us everything we need to calculate these values. It gives us a delta H value, it gives us a density of the fuel, and we know that the molar mass of carbon is 12.01 grams per mole. So the first thing we're going to do is calculate the specific energy. To do that, we just divide the delta H value by the molar mass. When we do that, we get 32.8 kilojoules per gram. Next, we can calculate the energy density. This is similar, but a little bit different because we have to multiply the delta H value by the density. And when we do that, we get 7.44 times 10 to the 7th kilojoules per cubic meter. Now, please note that I divided by 12.01 times 10 to the negative third because our mass value in the density was in kilograms, so our molar mass has to be in kilograms as well. All right, so renewable fuel sources. There's several that we're probably all pretty familiar with: solar and wind, fuel cells, which we'll talk about in option topic 4 for the HL class, water or hydroelectric or geothermal sources, and non-renewable which are finite sources, that's why they're called non-renewable, are obviously coal, oil, natural gas, and nuclear. Now, we tend to think of nuclear as being a renewable resource, or renewable source of fuel, just because it is known to be somewhat cleaner than the other three, but there is a limited amount of nuclear fuel to be mined in the Earth's crust, and so nuclear is considered non-renewable. All right, so let's talk about fossil fuels. Fossil fuels are called fossil fuels because they are born from the carbon, hydrogen, and carbon-carbon bonds contained in fossilized organisms. And this is an example of reduction in the classic case. So we're talking about the form of reduction where we gain hydrogen and lose oxygen. So in the living organisms, before they became fossilized, they had a lot of carbon, oxygen, carbon, sulfur, and carbon, nitrogen bonds. Now these bonds during fossilization have been replaced by the more durable and stable carbon, hydrogen bonds, which are broken and reformed in the fuel. So crude oil. Crude oil is the most important fossil fuel source that we have, because it gives us so many different forms of fuels to use. But it's really impossible to use in its natural form as it comes out of the ground. So crude oil is made up of smaller pieces that are known as fractions. So as the chain length of these fractions increase, we know the van der Waals forces will increase, the intermolecular forces. So various components of crude oil will have different boiling points. And the boiling points of these fractions can be used to separate them using distillation. Remember, we use distillation to separate mixtures of liquids based on their varying boiling points. So to do this, we use what's known as fractional distillation. And this is what's called a fractionating column. Now in this device, crude oil is input into the column after being heated. So we see that the boiling points of these substances decrease as we go. So once the fuel enters the column, the fractions that have very high melting point or boiling points will stay down below, where the ones that have higher boiling points will remain gaseous and float up in the column. So they will be separated in this way, and as they're separated, they can be drawn out one by one to produce the individual fractions of fuel. All right, so things at the top are shorter chain molecules, things that have very weak intermolecular forces, and they're great for fuels because they're very volatile and flammable, like butane and propane. Petrol is the European or British way of saying gasoline. And down below, the higher boiling point hydrocarbons will be more viscous, and they're not as flammable, so they're used for things like paraffin wax and asphalt. All right, so cracking. Cracking is a technique used to break larger hydrocarbon chains into shorter ones. Now, like we said in the previous slide, the shorter chains are more useful for fuels and such, so they take the longer chains and crack them into smaller, shorter chains. Right, so cracking is achieved by heating longer chains in the presence of a catalyst to break them into smaller and more usable pieces like ethene and octane. We know we can use ethene to make plastics, and octane is the greatest component of gasoline. So back in the day, cracking was achieved with steam alone, and they used alumina and silica catalysts. Today, the molecules are cracked and pass through zeolites. Now, the zeolites will produce a lot of higher octane 5 carbon to 10 carbon chains, which we know are useful in fuels like octane and gasoline. So this is just a picture of a zeolite. Now, you can see the structure of the zeolites. We have this sp2 hybridization, which creates these hexagonal ring structures in the zeolite. Now, these ring structures will allow straight chain hydrocarbons to pass through, but not branched hydrocarbons or longer chains because they get stuck on the holes. So the zeolites are used to separate the components. Okay, so here's an example from an IB exam. It says an alkane with a carbon number of 15 is heated over a catalyst and cracked, forming ethene, propene, and octane. State a balanced equation for this reaction. All right, so I want you to take a moment and pause the video and see if you can work this one out on your own before I go over it. Okay, so first thing we need to do is get the molecular formula of our alkane. All right, so we know that alkanes will have the general formula of CnH2n plus 2, and alkenes are CnH2n. So we're going to have to count up all the carbons in the products formed in the ethene, propene, and octane to make sure that they all add up to 15. Because if we start with 15 carbons, we're going to have 15 carbons in our products. So each ethene has 2 carbons, each propene has 3, and octane will have 8. So if we had 1 mole of each of those, we would have a total of 13 moles of carbon. Now we're going to need 15 moles of carbon, and so that means we're going to need 2 ethenes, right? If we had 2 octanes, we would have more than 15, and if we had 2 propenes, we would have more than 15. So we know that we have to have 2 additional ethene, or 2 total ethene molecules. So we'll write the formula for our alkane. Since we know the general formula for alkanes, this alkane will be C15H32. Next, we add our products, ethene, propene, and octane, and we put the coefficient of 2 in front of ethene to show that we're going to have 2 moles of that produced. And so that is our balanced equation. Easy peasy. All right, so octane rating. Now, in car engines, fuels are compressed in the pistons and then ignited with a spark. Sometimes the hydrocarbon fuels will auto-ignite during the compression phase. They call this knocking. And this is actually rather damaging to engines because if the fuel auto-ignites, it's going to throw all the pistons out of sync and it just kind of damages the works. So a measure of a fuel's resistance to knocking is known as its octane rating. And octane rating is what we see at the gas pump. Gasoline that's rated 87 means it has 87% branched hydrocarbons versus straight chain hydrocarbons. So effects on octane rating. As the amount of branching will increase, the octane rating then will also increase. So if we have 2,2,4-trimethylpentane, it will have a higher octane rating than octane even though it's an isomer because of the increased branching. And octane rating will decrease as the carbon chain length increases. So shorter chains will have a higher octane rating versus lower chains. So octane, the octane rating of hexane will be greater than that of heptane. So finally, the octane rating of aromatics like benzene is very, very, very high, greater than either straight chain or branched alkanes with the same number of carbons. Right? So benzene is put in gasoline because it has a higher octane rating than just about any other component put in fuel, including hexane or 2-methylpentane. All right, so catalytic reforming is a process that converts low-octane hydrocarbons, hydrocarbons with low octane numbers into branched hydrocarbons, which increases their octane number. So this isomerization is achieved by heating with a platinum catalyst. So the chains will break apart and reform, making more branched alkanes. Finally, we pass those products over a zeolite, which will separate out the straight and branched chains. So just a general example of this is breaking hexane apart and reforming a branched isomer. So we pass the hexane over a platinum catalyst through a zeolite, and we can form something like 2,2-dimethylbutane, which would have a higher octane rating because of the increased branching and the shorter main chain length. All right, so green energy. All right, so there's a number of different things we can do to make energy greener, and they're all laid out on this table. So one thing we can do, we talked about this in Unit 8, is remove sulfur from fossil fuels through scrubbing and filters. Right? Now that will reduce SO2 emissions. This will lower the amount of acid rain that we get, and that makes it greener. And the sulfur that's extracted can also be used to produce sulfuric acid, which is used in a lot of different industrial applications. Right. Another aim is to produce fuels with a lower environmental impact, so we can remove lead, benzene, and sulfur from gasoline, and they do that through the use of catalytic converters. Right? They do the catalytic reforming after the fuel is burned. So you get the benefit of having the higher octane rating of things like benzene, but the benzene is reduced coming out of your tailpipe because it's bad for everybody. All right, next aim is to produce alternative or blended petrochemical fuels. We see this at the gas pump where you see contains 10% ethanol. Right? They'll actually mix ethanol with gasoline, and that reduces overall carbon dioxide emissions from the gasoline because the ethanol is produced from the fermentation of plants. And during their life cycle, the plants actually sequester carbon from the atmosphere. So the energy that's released from burning those plant-based fuels are carbon neutral because all the energy that is released came out of the atmosphere originally. Finally, we're going to develop renewable and alternative fuel sources like bioethanol, biodiesel, electric cars, got to get me my Tesla, and fuel cells. All right, so coal gasification. This is basically the process of turning coal, which is essentially a rock, into gaseous hydrocarbons that we can use. So coal is a lot more abundant than oil, and it's actually easier to get at, so it's very, very desirable for energy companies. Now, gasification is the process in which synthesis gas is produced by reacting coal with oxygen and steam in a gasifier to create hydrocarbons. Now, synthesis gas is an overarching term that basically just means different carbon-based gases. So a lot of times synthesis gas is carbon monoxide or various hydrocarbons. Right? So the oxygen reactant that is used to gasify the coal is always in limited proportion, and so that is so that we don't fully combust the coal. Basically, the gasification process partially combusts the coal. And the process can be done underground so that the carbon dioxide that is produced in the process can stay underground. Now, this is an example of carbon capture technology, which is abbreviated CCS, or which stands for carbon capture sequestration. So CCS is a process that collects carbon dioxide from various industrial processes and injects it into rock formations. So it doesn't end up in the atmosphere, it goes into the ground. All right, so this is just a diagram of the process of gasification. Right? So the oxidants are brought in through a tube into a coal suppository, or repository, excuse me. So the coal doesn't have to be mined from the ground in order to be gasified in this way. So the reaction actually takes place well underneath the water table and doesn't produce the carbon dioxide in the atmosphere. The carbon dioxide actually stays down in these rock formations, and the gases, the synthesis gases that are used for fuels, can be removed, keeping the stuff we don't want underground. All right, so coal liquefaction is the process of turning coal into liquids. All right, so there's two types of coal liquefaction. Indirect, which is a process where synthesis gas is filtered and cleaned and added to water and carbon dioxide over a catalyst. Direct coal liquefaction, which we see more often, is when hydrogen is added to heated coal in the presence of a catalyst. All right, so both of these processes will adjust the carbon to hydrogen ratio to produce synthetic liquid fuels as a process known as the Fischer-Tropsch process. And this is shown by this general equation, where we have N moles of carbon monoxide mixed with 2N plus 1 moles of hydrogen to produce an alkane and water. And whatever the carbon number the alkane has will be the number of moles of carbon monoxide or synthesis gas that we start with. So there's two ways you can go about these problems if you have to produce these equations. One way is just know that in liquefaction the reactants will be hydrogen and carbon monoxide, and the products will be an alkane and water. But if you actually remember this general form, then the equations will come out ready balanced for you, and you won't have to worry about that, even though that's really not that much of a problem. So here's an example. It says predict the products and deduce a balanced equation for the liquefaction of synthesis gas to produce liquid octane. All right, so we know that our synthesis gas is carbon monoxide, and we're going to react it with hydrogen. All right, we're going to produce the alkane octane and water. So in this case, N is going to be 8. So the equation becomes 8 carbon monoxide plus 17 H2s, making your octane, and 8 moles of water. So again, if you have the general form, you get the coefficients, but if not, you just have to know that carbon monoxide and hydrogen are the reactants, and the alkane and the water are the products. And finally, carbon footprint. So carbon footprint is the measure of the net quantity of carbon dioxide produced by a process. Now, these carbon footprint problems are mostly just stoichiometry. So here's an example. It says calculate the carbon footprint in tons of carbon dioxide of burning 1,000 kilograms of octane. Now, when we see ton written like that, it's actually a metric ton, and a metric ton is 1,000 kilograms. So we have our chemical equation for the combustion of octane. It's already ready balanced for us here. All right, so we're just going to do some stoichiometry. We're going to take a mass of octane and determine the mass of carbon dioxide produced in tons. So the first step, we're going to convert the mass of octane into moles of octane by dividing by the molar mass. Now notice we're starting with kilograms of octane, so I just converted my molar mass to kilograms to reduce the number of steps I needed in this problem. Next, we'll use our mole ratio to convert into moles of carbon dioxide, and then we'll convert to kilograms of carbon dioxide. When we do that, we get 841 kilograms, which is 0.841 tons, metric tons. And finally, we can get a carbon footprint from delta H. Now, when we do this, we're not actually looking at the total mass of carbon dioxide produced, just the amount of energy released from carbon dioxide per mole of carbon dioxide. All right, so when we're given a value for delta H and a balanced chemical equation, all we have to do to calculate the carbon footprint is divide the delta H value that we're given by the number of moles of carbon dioxide produced. So a quick example, it says calculate the carbon footprint for the combustion of 1 mole of butane. So to do this problem, we would just need a balanced chemical equation for the combustion of butane. If we're given a delta H value, all we have to do is divide that delta H value by the number of moles of carbon dioxide produced in the equation, and we get that 4 moles of carbon dioxide for this process will produce 719 kilojoules of energy. I shouldn't say of CO2. It should just say kilojoules. Sorry, I hate to adjust my PowerPoints on the move, but sometimes you gotta do what you gotta do. Alright, so other processes will have different delta H values. So the one that releases the most energy per mole of carbon dioxide would be the one that has the lowest carbon footprint. And that is it for this discussion. Now, it seemed kind of rambling, one topic to the next, some interrelated, some not interrelated, and this is just how the option goes, okay? So we're going to do a much more thorough lesson in class. So if this video lesson confused you, please, 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 please just bring questions to class, and they will all be answered for you. All right, thanks for watching.